I'm Dean Eccles. I'm an associate director here at the Institute for Data Systems and Society, and really it's a pleasure to introduce our speaker for today. So Professor Jason Hartline is a professor of computer science and really working at the interface of computer science and microeconomic theory, mechanism design. He has a textbook that I know a lot of people refer to in this area on mechanism design and approximation that's been developing over a long period of time. And today he's going to talk about scoring rules for a theory of AI, which I've recently been fascinated with scoring rules, and so connecting them with AI. There's all this kind of hot connection in what is a topic that maybe a lot of people were interested in a while ago, but is incredibly relevant right now. So it's really a pleasure to have Jason here. Let's welcome Jason.
Thanks a lot. Yeah, it's been, got it. Okay, yeah, thanks a lot. It's been great. I've had a really great day meeting with many of you today. Yeah, I'm going to tell you today about scoring rules and a theory for AI. And this is kind of like summarizing, I think, sort of an emerging perspective that this idea of scoring rules, which many people are sort of independently turning to as a very useful mathematical way to mathematically understand the quality of predictions, is just going to be a very important thing to get a handle on as we try to understand AI. This is going to be combining lots of projects with lots of different people over the past about 7 years. And so just many thanks for my co-authors for leading me on this amazing journey. And especially every single paper we're going to talk about today in detail is part of Yifan Wu's PhD thesis. And she recently graduated, is just down the street at Microsoft Research. So if you find this stuff interesting, you want to talk to an absolute expert, she's the person to reach out to in your neighborhood. All right, so I want to just give you a little bit of background. So my field is from the economics and computation community that has been, for the last 25 years, been trying to develop an algorithmic understanding of economic questions. And so combining algorithms and incentives, for example, understanding if the algorithm's outcome is good, even when the inputs may be strategic, trying to manipulate the outcome of the algorithm is the main sort of thing of interest there. And so they model strategic agents, markets, and institutions to try to understand if these things are giving good outcomes. And this field has been incredibly impactful over its 25 years. There's this ACM Conference on Economics and Computation, which is sort of the flagship conference of the field. It's sort of underlying the development of online marketplaces with tech companies all sort of innovating in building these marketplaces that sort of build on these ideas and combining algorithms and incentives. And many research groups all over industry and academia, et cetera. And so my focus sort of before I got into understanding scoring rules in AI, which is the focus of this talk, is in auction theory and mechanism design, how to design the rules so that when people are strategic, good things happen, with applications to online marketplaces. So that's sort of been my background. Cool. So I don't need to tell you that there's a revolution happening in AI. You've noticed. And the pitch I want to make to you is that I think the thing that for 25 years, people in the EC community have been doing is going to be really important for developing a theory of AI. Okay, and let me tell you why. Okay, so the EC community has a theory for understanding complex human behavior and getting algorithms to work with humans, and humans are complicated. And we do that without modeling the complexity of humans, such as human intelligence. And so I think similarly, we can develop a theory for how to get AI systems to work well and reliably without having to understand the details of AI and the intelligence part of AI. And I think that's a really powerful idea that this community can help with. Okay, so the general approach that I'm recommending is that we repurpose simple models that we use in the EC community for understanding human behavior and apply them to AI, potentially highlighting key differences if there are any. Okay? And I want to point out that there's a field of machine learning theory that does lots and lots of great things. I'm talking about a complementary theory to that. I'm not replacing that. That still needs to develop great things. Okay? But I'm talking about answering different kinds of questions using the kind of high-level approach that people in the incentives and algorithms community use to think about these questions. Okay, and the simple model that I'm going to be focusing on in this talk is going to be proper scoring rules. Okay, and I'll point it out in a second, but proper scoring rules in my mind are really equivalent to Bayesian decision theory. And so this is like too many buzzwords at once, so I just want to focus on one of these buzzwords, which is proper scoring rules, and that's going to be just really the subject of my talk. But you know, different times I give different talk, I sometimes say Bayesian decision theory, I sometimes say proper scoring rules, but really to me they're the same thing. Okay, cool, so we want a theory of AI. And I could consider sort of EC style questions about the theory of AI. I consider ML theory questions of AI. And I think we want to be up here with lots of great theory. I think we're currently down here. And I don't want to overcommit in this talk, so maybe we'll be able to get a little bit up with some of the stuff I'm talking about today. But you know, I think the thing that I'm most excited about is the opportunity. The fact that these mathematical ideas might have a lot of mileage to go in what they might be able to do. And to me, that's very exciting. Okay, good. So I want to now try to tell you why it seems to be that scoring rules have a very big impact to play in understanding a theory of AI. Okay, so let's start with Bayesian decision theory. And I promise not to give you too many definitions, but let's remind ourselves what Bayesian decision theory is. And I claim it's a fundamental model for understanding AI. Here's what Bayesian decision theory looks like. Nature draws a state. The agent observes some signal that's correlated with the state. The agent then takes an action in the world and receives some payoff that's related to the action in the world and the state they take. And they can, you know, given the belief they have from their signal, try to optimize that. Okay, so that is going to show up all over the place in AI. Okay, next token prediction. The signal is previous tokens. The state is next token. And we want to receive a payoff for best getting a match of the next token. Supervised fine-tuning. The signal is this is a key step in the current LLM pipelines. The signal is the prompt. The state is the ground truth response. We want a model that does a good job, given the prompt, of coming up with something close to the ground truth response. Explainable AI. The signal is an AI recommendation and an explanation. Okay, the state is the state, and we want a decision maker to take the AI's recommendation explanation, decide whether to go with that explanation or do something else. Okay, prediction as a service. Here the signal is just a prediction, the state is a state, and we want decision makers who see this prediction to be able to follow the prediction as if it's true. Okay, so these are all Bayesian decision theory problems. And these are sort of fundamental, like all over the AI space. This is what's happening everywhere. So, and notice that I've given the first two things are inside the AI algorithms, and the second two things are sort of outside. It's like how we use the AI. And so these Bayesian decision problems are all over the place. Okay, and now here's how I'm going to get rid of Bayesian decision theory and just talk about scoring rules. Okay, so basically the revelation principle, which is a central idea in economic mechanism design, says that I can convert any Bayesian decision theory problem into a proper scoring rule. Okay? And how do I do that? Well, given a decision problem and the score I get for some, I'm going to define a proper scoring rule this way. The score for a belief is defined to be the payoff of the optimal action given the belief. Okay, so I just tell me a belief. I'm going to then optimize my action in the decision problem given this belief for the best score and define the scoring rule that way of just choosing the action that does that. Okay, and this is central in Meyerson's simple analysis of treatment of auctions in the 80s, and has made just colossal things possible in mechanism design over the past 45 years. And so this is just a much simpler object than Bayesian decision theory is an object, and so that's why I think it's sort of a central way to view these problems as they impact AI. So I'm going to be, in this talk, just talking about scoring rules with the idea that anytime I have a decision problem, I can convert it into an equivalent scoring rule and just study the scoring rule.
Do you want to conceptualize, like, in cases where the payoff is not known?
I don't want to talk about when the payoffs are not known today. In all these problems I've mentioned, the payoff is known. So doing next token payoff, we're trying to match the prediction of the next token. Doing supervised fine-tuning, we have a ground truth. The payoff is some way to evaluate the ground truth. So we have known payoffs. To talk about decision problems that are unknown is actually something we're going to be able to talk about later in the talk, but let's maybe defer the question till then. Actually, this prediction as a service problem, here the payoffs are not going to be known. Why is that? You have a predictor as a service. Some decision maker is going to potentially use your prediction. We don't necessarily know the payoffs of your decision maker. So that's going to come up exactly in that part of the presentation, so we'll see that then. Cool. So, good. So I said by the revelation principle, I might as well talk about proper scoring rules. And something I'll tell you I'm going to present later is that essentially if you look at mathematically what a proper scoring rule is, they're going to be mathematically equivalent to truthful mechanisms that the EC community has been studying for many decades. Okay, so a truthful mechanism is one where each agent, when they report, bid to in a auction, their optimal bid is to just say the truth. What is their true value for getting the item you're selling in the auction? A proper scoring rule is one where you're scoring predictions, and the best prediction is your true belief, according to the subjective belief that you have. Okay, and so there's a huge literature in economics and computer science about designing truthful mechanisms. And there isn't so much of a literature on designing proper scoring rules. And so one of the things we're going to talk about today is how to design good scoring rules. And the key difference in these problems is, well, the incentive constraints the same, but the things we care about and our objective that we might want to optimize over are going to be different. And so that's going to motivate new kinds of questions that relate to mechanism design. Okay, so for example, an objective that has come up time and time again in understanding scoring rules has been this one, this incentive for effort or value of information. Okay, the difference in score for your prior belief without the information and your score with the posterior belief with the information. So that difference in score has come up over and over again as a very salient objective to consider. And so then you could say, given some information structure where you have some prior belief and you get some signal and have some posterior belief, what is the scoring rule that optimizes this difference, this value of information, or the incentive of effort of collecting the information? Cool. All right, so that's sort of my overview of why scoring rules, I think, are a canonical mathematical framework that's going to be important for understanding the theory of AI. And now to give you sort of the plan for the talk, I want to first give you a short story of using scoring rules to do peer grading, which is something that I did in some of my classes for, almost a decade ago I started doing this. And then I claim that scoring rule design and mechanism design are basically the same thing. I want to present that to you. And finally, I'm going to go to the sort of the main agenda, which is some examples of how understanding scoring rules can help us build a theory of AI. So that's my plan for the talk. So let's jump in again, and thanks, Kostas, for the earlier question. Please jump in if you have any questions. So the short story about peer grading. So peer grading is, look, I want to assign peers to review each other's homeworks and give them grades. Okay, and of course, if you assign students to do any work in your class, you better grade the work they do. So you have to figure out how to grade the peer reviews. Okay, and so then oh no, maybe I wanted to do peer grading to not have lots of grading tasks, but now I have even more grading tasks. Now I have to just grade the original work and also all the peer reviews. Okay, so here's an approach. Maybe I could sample some submissions and have the TA grade these submissions. And then I could try to grade the peer reviews against the TA reviews using, I view the peer reviews as a forecast and the TA reviews as the state. Okay, and I want to grade them using proper scoring rules. Okay, so if my students, give me a bunch of numbers for different criteria for evaluation, my TA gives me a bunch of numbers. I then want to basically use the peers' predictions as a prediction of the state, the TA, and grade that way. Now, all my TA has to do is grade the submissions, and I can automatically grade the peer reviews. Okay, so let's review proper scoring rules just to make we're on the same page. So my TA, and let's just assume it's a single dimensional criteria, so just how good is the submission from 0 to 1. So the TA is going to have some score y, that's the truth. And the peer is going to have a belief p on the expected score of the TA for this submission after having a careful look at it. But then they're going to maybe make some other report R. And we're going to use maybe the quadratic scoring rule, which rewriting the quadratic scoring rule to be a positive value is good. It's 1 minus the square difference between the peer report R and the TA ground truth Y. Okay, so just to make sure we're on the same page, if the peer reports 0.8 and the TA reports 0.3, that difference is 0.5. 0.5 squared is 0.25. And so 1 minus 0.25 is 0.75. That's their grade for this peer review. OK, so if you know one thing about proper scoring rules, you know that the quadratic scoring rule is proper, meaning reporting R equals P, your true belief about the expected value of the TA's report, is the optimal strategy for you as a peer if I use the proper scoring rule. Cool. I'm going to show you a proof of this, because this proof of this is going to allow me to explain the geometry of proper scoring rules with a nice picture that's going to be all the geometry we need to know about proper scoring rules. So if you know one thing about proper scoring rules, it's that the quadratic scoring rule is proper. If you know two things, you know that it's characterized by convex functions. OK, so let's let U be this particular convex function, which I drew here so you don't have to read it. OK, and you could do some algebra to take this scoring rule and rewrite it in this way in terms of U. And how to do the algebra is not very interesting, so don't worry about it. But I can rewrite this as basically evaluating u on a supporting hyperplane plus some term kappa, which is only dependent on the state. Okay, and the key thing is if kappa is only dependent on the state, then our report doesn't affect it. So for incentives, we can ignore it. So for incentives, all we're doing is evaluating supporting hyperplanes of this convex function u. Okay, so if I report R, I'm saying evaluate the state on this red supporting hyperplane of this blue convex function u. That's what I'm saying. Okay, and so let's see why it's proper. Well, if I report R and my true belief was P, well, by linear expectation, if I believe the expected value of the TA's y is P here, and I evaluate myself on this red line, which is linear, I just get this amount, right, which is on that line. Okay, that's if I report R and the truth was P. But I could have reported P and then got it evaluated on this hyperplane, which would have a higher expected value, right? Because this is a convex function, so every supporting hyperplane is below it. So that difference between this value and this value is always going to be positive. Okay, so that is why the quadratic scoring rule is proper. So it turns out this characterizes proper scoring rules. So every single proper scoring rule for eliciting the mean of a distribution can be written like this. Okay, so it's always just convex functions and supporting hyperplanes. Cool. Let's go back to peer grading. All right, so I was like super psyched 10 years ago to run the quadratic scoring rule in my class to grade the peer reviews. And then I noticed this problem. Let's assume my TA is pretty much always going to grade between 0.6, basically failing, and 1. So 60% and 100%. Then here's a strategy you can take, which is actually very easy. I don't even look at the grading task. I just always say 0.8. Okay, well, if y is always between 0.6 and 1, and I always say 0.8, then the maximum difference is 0.2. 0.2 squared is 0.04. So I get a 96% by following the lazy strategy. And so that is not going to get my students to do any peer grading. So while the scoring rule elicited your true belief, it didn't incentivize you to get information. So there's very little incentive for effort here. So that led to my question, which became a research question for me, which is, are there better scoring rules? Can I put scoring rules into the framework of mechanism design and optimize over them to find ones that are better than the quadratic rule? So we wrote that as the following program. Imagine a simple model of effort in peer grading, a binary effort. So a peer in my class is either going to look at the submission and get a posterior belief, or not look at the submission, in which case their belief is the prior. And in a proper scoring rule, they'll just report the prior. Okay, and so I want to maximize this difference in score for effort and no effort, which is the posterior score and the prior score. Subject to, I'm going to keep my grades in my class between 0 and 1, so it's going to be a bounded scoring rule. Okay, so rewriting that a little bit more mathematically, I'm maxing over scoring rules, the expectation over the state and belief with effort of the score with effort and the score without effort. Subject to, scoring rule is proper, and the scoring rule is bounded. Okay, so we did this, and here is one of the results that we got. And so remember I said that scoring rules you can always characterize by a convex function, and the score is evaluating it on supporting hyperplanes of that convex function. And so here's what the single-dimensional optimal scoring rules look like. It's going to be V-shaped, and the kink of the V is the prior. So essentially what you're saying is, peer, is this submission above average or below average? If it's above average, you get evaluated on an increasing function. If it's below average, you get evaluated on a decreasing function. So an increasing function means the higher the TA grades it, the more score you get. And the decreasing function means the lower the TA grades it, the more score you get. So those are optimal scoring rules. And in fact, the standard scoring rules like quadratic are not even approximately optimal. So there's no factor in which they approximate this scoring rule. Yes, please.
So what in the example you had, like 0.6 to 1, there's no
Yeah, so the question is, why can't I just normalize my interval from 0.6 to 1 and make it better? You can, so it depends, right? So if I want my grades always to be between 0 and 1, and sometimes they're below 0.6, then I can't normalize it. Okay, and so really the boundary is going to come into this boundedness of my scoring rule. I want it to be bounded everywhere, and so I need to basically have the full range. Yeah, that is not the main reason why the quadratic is bad. That was just that one example. The real reason why the quadratic is bad is because you could have signals, the state distributed on a very small interval, and that's where the quadratic is going to be very bad.
You used to decide, what score to give up the numbers on the equation? Like you use the prior distribution to decide how much to give?
Yeah, so the optimal scoring rule for the single dimensional problem only depends on the prior. And I'm bounded, so I've got this between 0 and 1. I can, without loss, start it at 1 and have it slope down and cross at the prior. Okay, so one cool thing about this theory is you don't even need to know the posterior distribution. You just need to know the mean of the posterior distribution, which is the same as the prior distribution. Okay, I'm going to show you the proof of this theorem, because I love showing proofs, and also it's by picture. Okay, so let's suppose I have a scoring rule that I think is good. What I'm going to show is that if I make it V-shaped, I improve it. Okay, so consider any ex post bounded scoring rule defined by some convex U. So here I've drawn one. And then let's think about replacing it with a V where the kink of the V is at the prior. Okay, I claim that the objective I have, which is the expected value of U on the posterior minus the expected value of U on the prior, weakly increases. Okay, well, first off, red is always above blue everywhere, so your expected value for any posterior belief is only higher. Okay, and U of the prior is unchanged. It's the same value as it was on the blue. Okay, so this objective weakly increases from this change. So I also have to check boundedness. And boundedness comes from how extreme the supporting hyperplanes are. And when I had the blue function, I had these extreme hyperplanes here. And when I inscribe it with this V-shaped thing, things get less extreme. So if it was bounded before, it's bounded now. Cool, that's the proof. Okay, so what have I done so far? I've shown you how to optimize scoring rules for effort. They give you these V-shaped things in a single dimension. In the papers, we have multi-dimensional versions of this theorem, which is a generalization, but I'm going to skip that for this talk. The next thing I want to talk to you about is this connection between design of scoring rules and mechanism design. And again, mechanism design is an area that we've been studying for many, many decades in the EC community. And shockingly to me, this approach hasn't been applied very much to scoring rules. And so I think there's a lot more to do in applying this to scoring rules. And so I will say this Frangeo and Cash paper does a good job at comparing this is like the sort of the reference you want for understanding this scoring rule design is mechanism design. And so let me just, again, write down this program we had before. For scoring rule design, we're going to be maximizing of our scoring rule, some objective, subject to properness, and maybe some constraints like boundedness. And McCarthy's 1956 characterization of proper scoring rules is the following. It's proper if utility as a function of the agent's forecast is a convex function, and the score that I get in any state is evaluating on a supporting hyperplane of this convex function. That's the picture we were drawing before. Okay, what does mechanism design look like? So this is a typical statement of a mechanism design problem. We want to maximize over mechanism, some objective, subject to the mechanism is truthful, which is basically the same thing as properness in scoring rules. So that truth telling is an equilibrium in the mechanism. And maybe some feasibility constraint, like if I'm allocating items to agents, then I don't allocate more items than I have. That would be a feasibility constraint in mechanism design. Roche in '85 characterized truthful mechanisms in multidimensional settings as the utility as a function of the agent's value is convex. And the allocation is a subgradient of utility. And if I shift that allocation up to be a supporting hyperplane, then the amount I shifted up is the payment. So we allocate to them to supporting hyperplanes, and we charge them an amount that shifts the hyperplane up to be a supporting hyperplane of the utility. So basically, convex functions and supporting hyperplanes characterize both properness and truthfulness. And the main thing that makes scoring rule optimization different then is going to be what our objectives might be if we cared to optimize them. So for scoring rules, maybe we want to maximize the difference in score from the posterior and prior, like we were talking about, or you maybe want to maximize some kind of accuracy if you're measuring, if the scoring rule measures accuracy. For mechanism design, we typically are looking at things like welfare or revenue, which are just quite different objectives. Like if I said the payments are how much you shift these hyperplanes up here, so you're maximizing how much you shift the hyperplane up, which is just a different objective from the scoring rule problem. Cool. And so I find this connection pretty exciting because optimizing scoring rules is very underdeveloped. Optimizing mechanisms is very developed, and we've lots of great things we've learned from optimizing mechanisms that we can potentially learn on optimizing scoring rules. Cool. So now is a good time to review some of the literature. So a lot of the early work on scoring rules in statistics was basically characterizing properness, and so a bunch of early works looking at doing that for various settings. There's some old work on optimization of the quadratic scoring rule and some optimization from costly samples. And then, after we wrote this sort of binary effort paper, lots and lots of works found applications of this framework of optimizing scoring rules for binary effort, and it's become like really a nice area of study. Cool. All right, that's sort of like the background, and now let's turn to the main event.
So some various barriers for multidimensional mechanism design. Do similar barriers arise in designing multidimensional scoring rules?
Yeah, so it's a great question. Some of the scoring rule problems tend to be simpler even in multidimensional settings. So for example, it's pretty easy to write down the simple, like imagine you're predicting a multidimensional state. That scoring rule for binary effort, that's pretty easy to optimize, turns out. There's a simple characterization of that. It basically ends up being like a knapsack problem. Which is sort of a nice algorithmic characterization. A fractional knapsack problem, which is a nice algorithmic characterization. This paper, which looks at multidimensional state and effort, so imagine we have a multi-dimensional state, and we can put effort to learn a posterior on each dimension of the state, instead of just a binary effort to get the whole signal at once. And there things get really quite complicated very quick. And so like in a more technical version of this talk, I sometimes go into our inability to solve this problem very well. And so that would be an area where I think that there's a lot of sort of technical work to do in understanding how to get things to work. And the model we were able to solve in this paper is actually a much simplified version of the model, and you'd really like to have it be a more general model. Cool, let's talk about scoring rules for a theory of AI. And so just to remind you some of the questions that I think are interesting in AI that relate to scoring rules. And so I've listed these A, B, C, D here. And so what I plan to do next is first talk about prediction as a service, and then explainable AI and supervised fine-tuning, which are D, C, and B. Cool. So this is a paper by Linjia Hu and Yifan Wu. So they're both in the Cambridge area. Linjia just started at Northwestern on the faculty, and Yifan is at Microsoft Research as a postdoc just down the street. So I encourage you to reach out to them if this is a topic that you find especially interesting. So they have this amazing paper, Calibration Error for Decision Making. And so basically, this is in the prediction as a service problem. So we have a predictor, maybe it's the weather forecaster. They're making predictions about the probability of rain. How do we evaluate whether those predictions are good? Okay, and the one of the nice ideas is that if you measure calibration, which I'll define in a second, and if the calibration error is small, that means that if decision makers just follow the prediction as if it's true, using the optimal action for the prediction, that means they will have low swap regret. So basically, calibration sort of is going to correspond to swap regret. Okay, and good. And so this paper is basically giving a new way to define calibration error that makes this connection to swap regret exactly precise, and in particular, not overcount. And the problem with overcounting errors is it means if you try as a predictor to minimize this calibration error and you're overcounting, it means you need much more data to minimize this thing. So the sample complexity is going to be higher if your error metric overcounts error. And so having a tighter notion of what the actual loss is going to be is going to help you lower the statistical complexity of the tasks you have in hand. Okay, so let's get into the details. So imagine we're doing online binary prediction, P of some state Y, like bad or good. So imagine it's like taking an umbrella or not, and it's raining or not for decision making. And here's the key thing. Different decision makers might have different decision problems. So like maybe you want to take an umbrella if the probability of rain is above 1/2. Someone else needs to take an umbrella if it's different. Maybe Uber needs to like have more surge pricing for cars if the probability of rain is above, whatever, and it's going to be a downpour because they need to get more riders there. So everyone's got a different decision problem. Okay, and I want this prediction to be good for all decision makers. So the standard notion in the literature for measuring calibration error is this expected calibration error, which is the expected absolute difference between our prediction P and the posterior conditioned on our prediction P. Okay, so in other words, if we make errors in our prediction, that means given my prediction, we can sort of Bayesian update and get a better prediction. So P hat is my Bayesian update, and P is my actual prediction I make. Okay, and we just measure the absolute error in those. So what they did in this paper is define a different notion of calibration error. They called it calibration decision loss. And this is just literally the swap regret of the worst case decision maker. So in other words, if we look at all decision makers and we look at the difference that basically their loss from following the prediction versus optimally taking the action for the posterior of the prediction, which is the best way to update. Okay, what is that worst case loss among decision makers? And we'll make the error be the worst case loss.
So online setting, are you considering like a...
I'm considering an online setting.
Online
Setting is online binary prediction.
Online,
Yeah. I mean, this error metric is, you can define it on offline settings too, but let's focus on the online just for now. Okay? And here's the thing. As I said, decision problems are equivalent to scoring rules. So the worst case decision maker corresponds to the worst case scoring rule. So if we can optimize over scoring rules, we can find the worst case one to figure out what this CDL is. Okay, so we want to optimize over score for the empirical posterior, that's this p hat thing, minus score for the prediction. Okay, and what they show is a relaxed version of the theorem I showed before. So I showed you for prior versus posterior, V-shape is optimal. What they show is for this calibration error, now we have two predictions. We don't have a prior here. Okay, so this is the score with the prediction and the score with the Bayesian update of the prediction. Okay, that difference is within a factor of 2, V-shape is optimal. Okay, which means by measuring errors, I usually don't care about factors of 2, so I can measure error just as twice it and get an upper bound on this decision-making loss, and that's going to be good. But I can understand how the ECE is overcounting from understanding this characterization by V-shaped rules. Okay, so they use this to show that CDL you can online learn with essentially the optimal rate of square root t, the statistical optimal rate, whereas there are lower bounds for online learning ECE that are worse than square root of t. Okay, and the big idea is that ECE overcounts calibration error. So let me give you a picture of how that works. So if this is my V-shaped rule, that's the worst case V-shaped rule. And imagine I've got these 4 different predictions. So P1 is my prediction, but the truth was P hat 1. And P2 is my prediction, and the truth was P hat 2, et cetera. Then if I notice for P4, both those predictions, you choose the same hyperplane here, which means actually there's no error in that, no loss to you as a decision maker from that misprediction. The only predictions that have loss for me in this decision problem are the ones that cross the tip of this thing, where I make the wrong choice of hyperplane. Okay? So what CDL does is it says, look at all these errors and find the place to put the tip of the thing to make it the worst. So the one where the tip makes things the worst. But it's only going to count the one of them, the one tip. Okay? But ECE, on the other hand, just sums them all. This sums all of the differences between the predictions and the posterior beliefs. Okay, so ECE is summing this, and CDL is summing this. Okay, and their characterization of V-shaped scoring rules tells you that if you want to do prediction as a service, it suffices to measure error with V-shaped scoring rules. Yes, please.
Not mathematical. I'm trying to understand how you score a weather prediction. I mean, it depends. Is it going to rain? Well, where is it going to rain? And how close is it? Microclimates, or how much is it going to rain? Or if it rains 10 minutes later than predicted, is that an error or is that sufficient? I mean, it's very hard to know what it is you mean by having an error. I mean, I'm having a hard time visualizing how you see that error.
Yeah, so
and then, of course, because you now are concerned,
definition,
your dispatch of Uber to make sure there are enough cabs or whatever, or vehicles in the right place at the right time, what does it really mean?
Yeah. I want to focus on binary prediction for this problem. But you could ask a question that wasn't binary about predicting the weather, which means I want at every point in time, at every place, was it raining? That's a multi-dimensional version of a prediction problem. Okay. Let's ask the binary question first, where we're wondering at a specific time in a specific place, is it raining? Okay, and there's a very well-defined meaning of what it means to rain there. Okay, I don't think.
I'm not quite sure about this. I'm just sort of wondering this because, yeah, I know what a downpour is, and I know what a sunny day is, but is it a Scotch mist? What are we really talking about? What is the threshold for this?
Or I guess, I mean, another way of characterizing some of this is you might think that if you were doing the full Bayesian decision theoretic apparatus here, you might think that somehow the specific decision that this forecast is being used for is sensitive or insensitive to some of those features or not. But the hope is that we substitute in this kind of maybe somewhat generic scoring rule that will work for all the downstream uses of this prediction. Or
yeah, so when you're making predictions about complicated events, like when and how much it's raining where, that's a very high-dimensional prediction task. What we're
trying to do that kind of thing to get the grab taxi out of the right place and so forth.
I'm not going to have any answers that are going to make you happy. Okay, and it's because what I'm after here is something different. I'm trying to understand how we should evaluate predictions that could be wrong. Okay, where it's going to help us get clarity about understanding predictions that could be wrong by considering the simplest kind of prediction problems first. Okay, so I don't want to get too distracted about the complexity of predicting a multi-dimensional weather event, because that's going to be a distraction from understanding what we actually care about in this, or what Linja and Ifan cared about in this paper, which is understanding binary prediction, which means you've already decided what the event was, and you've already decided what it means to have it happen or not, and we're just evaluating binary prediction.
I guess I'm confused by taking that problem and referring to the weather, because I think, as I understand it, weather is not a binary prediction. It's not like does Arsenal beat another football team or something? Who wins? It's yes or no. I know what the prediction is, but weather is not binary. That's maybe my confusion. I'm trying to understand how.
I understand your confusion. And so pretend we're predicting football.
Right. So that puts, that I can understand, this or that. There is a truth to it.
Great. We're predicting football, and we're trying to determine whether we want to bring our celebratory equipment to the game or not. Different decision makers have different costs of bringing all this celebratory equipment to the game.
How does the CDL relate to like maximum calibration error, like the maximum gap from the, if you draw the like reliability diagram, you can look at the max. EC is averaging across it, you can also take the worst case gap.
Yeah, so this is going to be different from the maximum gap because it is averaging only the ones that go across, it's basically averaging, but only the ones that cross the tip of the thing. So things that are where the truth and the prediction are entirely outside don't even come in. But it's looking for the most things that cross one line and averaging those.
But it's like the worst case location for the...
Exactly. It's the worst case location for that kink.
Is that going to be related to the place where the reliability diagram is maximally off the peg?
No, because probably the place where it's maximally off is going to have a signal that's got a very wide error, but there might be other things with little error that aren't off that also cross the tip. So it's going to sum several things. Basically, if you take that reliability diagram and draw a horizontal line in it, you want to cross as many of them as you can, or the most weight of them as you can. Okay, and in the reliability diagram, they don't show you the frequency of each one, the weight of each one. And this is weighted by the distribution. So you basically want to take the reliability diagram, weight it by the distribution, and draw a horizontal line and see where do you cross the most of them. And actually, it's not even that because you have to actually look at the distance. It's the distance in the thing weighted by how many things cross that line. question. Thank you. Cool. So I want to tell you about decision. This is closing down that topic. I want to tell you about a decision theoretic framework for measuring AI reliance. Here, the information we're talking about is an AI recommendation and an explanation. So imagine the AI recommends some action, and it also gives an explanation for why they recommend that action. Maybe you should look at these X-rays, and maybe you say this person does or does not have a tumor, and you give an explanation for why you think that it has a tumor. And we want to understand sort of human AI decision making and complementarity. And so what does this paper do? It's sort of using a decision theory framework for understanding AI reliance. Do we rely on the AI at the right rate or not? And so here's sort of the way to think about that. If I imagine the human alone at some decision task, they're going to get some performance. That's using the information they have, making the best decisions they can. How well do they score if we measure this in payoff space? Maybe it's like correct diagnosis of a disease. Okay, then we could take the AI alone and say, if we just let the AI make its decisions, how well does it score at this decision task? Okay, and then we can give a decision maker both the human recommendation and the AI recommendation and explanation and see if they do better. That would be complementary performance. Okay, so here, the signal we're talking about is the human recommendation, the AI recommendation, the AI explanation. And the action we're trying to figure out from this decision maker is, do I take the AI advice, or do I go with my own human instinct? Okay? And so the thing I want to do is imagine that we basically take the signal X as a signal, do Bayesian updating, and figure out what is the optimal thing to do given that information. So if we replace this behavioral decision maker who looks at what the human would do and what the AI would do in the explanation, and then makes their own decision, what if we replace that with a rational agent who's optimally acting given the statistics of the problem? So they would get what I call the posterior optimal score. Okay, and what we have been doing in the rational agent framework is looking at the difference between what we could do alone, which is the better of the human and AI. I call that the rational baseline. And what we would do if we took the signals and made the optimal decision, that's the posterior optimal. And so I call the rational baseline, the AI, in this case, it's the better of the human and the AI, which in this case is the AI. And the posterior optimal, that's the rational benchmark here. And then we can basically see in this plot how good was the behavioral decision maker compared to the posterior optimal. This is what they could have gotten if they'd actually used the information they had well. Okay, so the complementary value is sort of like how much is there on the table, and then the behavioral agent gets some amount of that. Okay, and so. Yeah, so again, we're evaluating decision making, and there's some payoff from your decision making problem. And it could be symmetric, it could be just false, minimize false positives and false negatives. Or it could be some asymmetric payoff, maybe misdiagnosing, maybe not treating when they don't have the illness is worse than, when they have the illness is worse than treating when they don't have the illness. So maybe it's asymmetric. Whatever your payoffs are from your decision problem, we're going to use those. Okay, so a bunch of papers in this space have been trying to understand under or over reliance. Okay, in other words, if this decision maker is not achieving as good as they can do, is it because they're over or under relying on the AI prediction? Like, are they, more often than not, are they just turning off their brain and just going with what the AI says when they shouldn't have? Or are they ignoring the AI when they actually really should have gone with it? Yes, please.
Again, what is the posterior optimal?
Yeah, so in Bayesian decision theory, I am given a signal, which I've called x here. And if I have all the data, I can Bayesian update on x and the outcome y. Exactly, all of the data. So basically, if we've done a behavioral study, what do we have? We've asked a bunch of people for a bunch of decisions. We have, for every decision asked, we have what the human recommended, what the AI recommended, and we have the AI explanation. So that is a bunch of data we have. Okay. We also know the ground truth, why, what happened. Like what was a tumor or not?
And AI here, they act as some sort of filter, like they view the property that you have and they give you some recommendation.
I can't hear you. Can you?
I mean, just like intuitively speaking, the human AI here, they are through like filters, like they filter the property and they give you some decisions or recommendations based on their own knowledge, and then you try to decide whether to trust them or not.
Yeah, so I want to understand human AI decision making. And so I look at what the human would have done alone, what the AI would have done alone, the AI explanation, and I ask if a human decision maker who has access to all of these can do better. Okay, so the thing I really want to tease out is, are the errors come from over or under reliance, or are they coming from something else? And we can do that in the following way. So I'm going to define the misreliant optimal behavior as the rational optimal behavior constrained to the same reliance rate as the behavioral agent. Okay, so if you look at the Bayesian optimal decision maker, they go with the AI or they go with the human at some rate. If you look at the behavioral agent, they also go with the AI or they go with the human at some rate. Okay, so what if we constrain and if they're different, then part of the loss is due to having the wrong rate. Okay, so we can ask if we just optimize the best decision constrained to have the same rate, where would that fall in between these two? Okay, and that's the misreliant optimal, and you can then categorize the loss between reliance loss and discrimination loss. Note, if the misreliant opt is very close to the posterior opt, that means even though we had the wrong rate, it didn't matter. With the same rate, you could have gotten just as well. On the other hand, if the misreliant opt is close to the behavioral loss, that means your error is from misrelying, right? Because if we try to optimize subject to that rate, we're stuck down here. Okay, and the reason why you want to, so if you don't have reliance loss, because if this is up here, all of your loss is discrimination loss. You're relying at the right rate, but you're not relying at the right times. You're not choosing when to go with the AI or when to go with the human decision at the correct times. Okay, and understanding which case it is actually important for interventions, because if it's reliance loss is the most loss, then you want to basically help the agent understand that they're either over-relying or under-relying, and they should put more, understand that the AI is either better than they think it is or it's worse than they think it is. Okay? If it's discrimination loss, that means your explanations aren't good. The agent isn't able to see the explanation and use that to know whether to go with the AI or go with the human recommendation. So, there was a huge behavioral literature on this, and you can take this framework and apply it to some. I'm over time. I want to stop. So let me not show you the experiments. We applied this to some experiments, and from this framework, you can basically find things that weren't in the original papers that were studying reliance themselves, and observe new things from applying this framework, which we thought was very useful. I'm going to skip the last part too, and my literature review, and just conclude with this slide. Yeah, sorry, there were more questions in the middle than I anticipated. But thank you for your attention.